So now we'll discuss the universal shift register. Whatever we discussed till now, all the registers, all the circuits will do only one operation, either serial in serial out, or serial in parallel out, or parallel in parallel out, or only one direction like shift right or shift left, or bidirectional, but not all in one place. So universal shift register does all the jobs like shifting left to right or right to left, parallel into serial out or parallel into parallel out, serial into parallel out or serial into serial out. So all kind of operation can be performed by using universal shift register, which will be available in IC form. We'll see that IC is a later part. First we'll see the internal operation. Universal shift register will have a multiplexers. These multiplexers assign the job to the shift register, either no change state or shift right or shift left, depending on our requirement. Now we'll see what are those control inputs, how the circuit going to perform that particular action in a moment. Now if you look at here, this is a black diagram of your universal shift register. You are going to have input bits at this place, you are going to have output bits, and your S0, S1 are control inputs, and you have a clock and clear input, and this is your LSB in, this is MSB in. Now if you look at here, this is a 4-bit shift register. You are having 4 D flip-flop. 4 D flip-flop are assigned with a clear input. Whenever we want to clear these 4 flip-flops, we can clear it by applying low pulse to this particular input. Similarly, if you look at here, there is a clock. Clock is applied to all the D flip-flops. Now here comes the story where you are going to use 4 into 1 multiplexers, and you have designed the connection such a way that it is going to perform the required action. Okay, now you can see here these are the A1 to A3, A0 to A3 as your parallel outputs, and your I0 to I3 as the parallel inputs. And similarly, if you look at here, there is one serial input for the shift right operation. That means the data will shift towards this side, and there is a serial input shift that will shift the data to this side. Now we are going to see how it is going to perform the operations one by one. It's just a simple manipulation with the multiplexers, how your data will be transferred or moved between the flip-flops. Now let us start with 0 0. So when S1 is 0 or 0, when both are 0 0 for 4 into 1 multiplexer, listen carefully. When both are 0 0, this 0 will be activated, this 0 will be activated, this 0 will be activated, and this 0 will be activated. That means whatever the data is here, the same data will be transferred to D bits. So before we start the operation of shift register, we are going to clear all the outputs. That means you are going to have 0 here, 0 here, 0 here, 0 here. When you give both 0 0 here, whatever the 0 here, that 0 comes here, and the 0 will again apply to the D flip-flop, again it comes here. So that means your A3 is not going to change. Whatever A3, it will be in the same state. Similarly, when both are 0 0 and this 0 will be activated, that means whatever the A2 output comes here, this 0 will be given to this D input, again it goes here. This cycle will continue. So that means whatever the A2, the same A2 will be circulated between your 0 input of the multiplexer and D input of the flip-flop. Same thing here also, your A1 will come back here, your 0 will be activated, this 0 input, whatever the data that will be transferred to D input, again it will appear at the output side. Same with here. That's why your 0 0 is no change. Whatever A3, A2, A1, A0 values are there, they are simply circulating in one full circle. It will goes from here and apply through the multiplexer and given to input as a D flip-flop, and it will appear at the output side. So that's why when you apply both 0 0, it's going to be no change state. Now if you look at here 0 1, when you apply 0 1, your the number 1 line is activated, this is activated, and then this is activated, and this is activated, and this is activated. If you look at here, when 1 is activated, when the clock is enabled, you are going, this 1 input is connected to the serial input. That means whatever the data you are going to apply in the serial fashion, that will be connected through this multiplexer. Since you are enabled first line, this will be connected here. This will be applied to D flip-flop. Whenever the clock goes high, the D flip-flop will take the serial input and apply up. Whenever the clock goes high, the same output, the same input will be displayed here. If you look at here, this feedback, it goes here, and if you look at it, it is applying to the one input of the second flip-flop. That means this data, whatever data you are applied, this will goes from here and goes out and comes here and goes here and apply to the second multiplexer. Since you applied 0 1 a select line, this again 1 will be activated. This one goes here and appear here, and this comes here, and this will goes here and apply at one input of the multiplexer again. This data will be again applied to this flip-flop. This will come out and it will come out here and again applied to the one input of the flip-flop. So one input of the fourth flip-flop. This will apply at this place and it will come out. So that means one data bit will travel from this to this multiplexer to D, and D to A3, A3 to this one to A2, and A2 to this one to A1, and this one to E1, and this one to A0. This for one bit. If you have a second bit also follow the same path. It will pass through 4 into 1 multiplexer, then applied at D, then appear at A3. A3 will be applied as input for the second multiplexer at one input line, because you activated one line, you activated the number 1 line, and will pass through D and appear at the A2. Again it fed back to one input with the third multiplexer, and it goes on. So when you make 0 1, your data is traveling from serial input of this place to taking this way and this way, this way, this way, this way, this way, and this way. That means your data is shifting towards the right side. Now if you make 1 0 means 2. If you look at here, this second line will be activated, this second line will be activated, this second line will be activated, this second line is activated. If you look at here, this second line is connected with the serial input. Now whatever the data you are applied to, that will be passed through this D flip-flop. This will be appear at the A0. Whatever the input, that will pass through this multiplexer, applied to D flip-flop, it comes out. Whatever data comes out, if you look at here, this loop, it is coming here and applying as a second input to this multiplex. That means the same data will be transferred to this D flip-flop. It will appear here again. This will go back and apply the second input to the next multiplexer, and it will apply to the D flip-flop. Again it goes back to the third multiplexer, the second input. Again it will apply to D flip-flop. It will come out at A3. So that means your data is traveling from this to this, then comes back and apply here and goes here and comes back this way and appear here and goes out and comes back here and appear at this place again coming out. That means your data is traveling towards the left side. That means you are shifting your data towards the left side. So next bit will be follow the same path. Now if you make both 1 1, when you make both 1 1, if you look at here, your third line will be activated, your third line will be activated, your third line will be activated, your third line will be activated. If you look at here, all these third lines are connected to the parallel input. That means whenever you apply 1 1, this line will be activated. Whatever the data here, that will be transferred here. Same data will be transferred here. This data will be transferred here. This data will be transferred here. Whenever the clock goes high, whatever the data appear at these 4 flip-flop, that will be transferred to the outside. That means your parallel input data will be transferred to the parallel output side. So this way we are able to achieve parallel in, parallel out, serial in, serial out with left shifting and right shifting, and similarly serial in and parallel out also possible, depending on how you take the output, at what clock cycle you take the output, that decides your parallel output. This is the universal shift register. Now I am going to demonstrate the working of universal shift register using assimilation software. Now let us see the universal shift register, which is IC 74194. As you can see here, your ABCD are the parallel inputs, and SL and SR are shift left and shift right, and through which we are going to input our serial data, which is going to be left shifted or which is going to be right shifted. And these are the four outputs of the 4 D flip-flops, and your S0 and S1 are your select lines. There is a clear to clear your outputs, and there is a clock to synchronize your operation. Now we'll try to see the operation of your. Now let's start our operation. So these are my parallel inputs, D0 to D3, and this is my serial data input, which is going to be left shifted. This is the serial input data, which is going to be right shifted, and these are my select lines. Now if you look at here, it's already having 1010 output at the output lines. I'm going to make it clear. Let's run the simulation. I'm going to make it clear. Now everything is cleared. Now I'm going to make first both 1 1. When both are 1 1, it's going to be parallel data operation. Whatever the parallel data here, that will be transferred to the output side. So let me make my parallel data as 1 1 0 1. This 1101 will be transferred to parallel output side the moment I make clear to 1. When I make my clear to 1, your control lines will enable the parallel in and parallel out operation. We'll see in a moment. Now you can see here 1101. This parallel data is transferred to the output side. Okay. Now I'm going to make both 0 0. When I make both 0 0, if you look at here, the same data is staying back. There is no change. Even if you change your data inputs, whatever the data you change here, these data change not going to affect your output. That means 0 0 is a no change state. Now I'm going to make 0 1. So before that, let me clear my output. Now it is cleared. Now I again make 0 0 no change. Now I'm going to select 0 1. 0 1 will be, let's make it my shift serial input both 1 1. Let's make it 0 1 now. Now you can see here it is shift right. Your data will be shift towards the right side. First 1 came here, then shifted here, then shifted here, and shifted here. This is the 0 1 select line. If I make 1 0, let me clear it once. Let me make 1 0. Now it's going to be left shift. That means your Q3 will come first, then data will be shifted towards this side. Now you can see here your one input is getting shifted towards the left side. This is with 1 0. If I make all 1, and it's going to store the whatever the data you are having. If you look at here, this is 0 0 1 1 0 0 1 1. So it's parallel in and parallel out. If I make 0 1 shift right, so your data will be shifted towards the right side. Yeah, you can see now your data is shifting towards the right side. If I make 1 0, now your data going to shift towards the left side. Let me clear it. Now you can see towards this side. My clock frequency is 1 Hz. If I make both 0 0, it will be in the same states. This is how your universal shift register does serial in, serial out, parallel in, parallel out operation in one IC. Now let us talk about the second IC shift register, which is a parallel in, serial out shift register. In this, your A to H are your parallel data, and SH/load will be shifting as well as loading your data. This 10 and 15 we are not going to use for our lab session, and this your clock. Now whatever the data you are going to give here, this is a parallel data, this will be transferred to the output at 9 port in a serial fashion. Let's make it 1 0 1 0 1 0 and 1 0. Now I'm going to run the simulation. My clock frequency is 18. That means every 1 second your output will change 1 to 0, 0 to 1, 1 to 0 and so on. Now let's run the simulation. Now here your shift and load is 1. First you have to load the parallel data. To load the parallel data you have to make load to 0 first. So now your data is loaded. Now you make it 1. Now you can observe your output 1 0 1 0 1 0 1 0. So you can clearly see now whatever the data you have given, that is again transferred to the serial fashion. Now we'll make the data to slide change. Now let us load 1110 and 1110 and let's check. Now your data is loaded 1110 and 1110. Let's make it shift. So 0 again 0, then 1, again 1, again 1, then 0. So again we'll test it. Now load once again. Now 1, 1, then 0, then 1, again 1, again 1, then 0. So if you clearly see, your parallel data is getting transferred to the serial fashion. This is all about your parallel in, serial out shift register. Now let us discuss the flip-flop timing considerations. So what are the different timing parameters one need to consider when you consider the design of a circuit or design of any shift register counter in practical applications? Why you need to consider the flip-flop timings? So at any point of time your output of your flip-flop depends upon your input as well as clock. This is for whatever we consider till now, but in practical circuit we need to consider other parameters. So we'll see what are those other parameters which we need to consider designing a circuit with the flip-flops. So these are the important parameters or timing parameters one should consider in designing a digital circuit. The first one is the setup time, then hold time. There are propagation delays for the clock as well as our input. Then what is the clock frequency you are supposed to use, and what should be the pulse width, and what is the clock skew. We'll discuss one by one what it is and what is the role of these parameters in designing the circuit based on flip-flops. So before we start the timing consideration, we'll first give a clarification. Whatever you have seen your digital signal till now are in square shape, proper square shape or proper rectangular shape depending on the duty cycle. But in real time circuit this is only ideal, this ideal waveform. But in real time you are going to have a clock something like this. If you look at your Walkerly book, you are going to see all the waveforms, all the clock signals something like this. So what it means, your clock will not go from 0 to 1 all of a sudden, or 1 to 0 all of a sudden. It takes some time to move from 1 to 0 or 0 to 1. Similarly, whenever the clock output, let's say you are having Q output for a flip-flop, it will not go something like this, 0 to 1 or 1 to 0. It will also goes in the same fashion, 0 to 1 and 1 to 0, so on. So, okay, so there are a delay from going from low to high to low. Okay, so this you have to consider when you design a practical digital circuit based on the flip-flops. Now we'll see what are the parameters one should consider for this clock signal or for this data signal. First one is the setup time. So if you look at here, the setup time is nothing but you have to keep your input setup time. In setup time you have to keep your input constant for a certain period of time before your clock comes into picture. Please remember, look at here, this is your clock input, and this is your synchronous input, that is your data input, and this is your data input, this is your clock input, and your setup time is defined from the 50% of your waveforms all the time for the clock as well as data also. If you look at here, from this point to this point, during this period your input should be maintained at a stable output level. So if you look at here, in this case your output is stable at 1, so it will take, your circuit will take this input as 1 and respond accordingly. If you look at here, during this period of time your input is above logic 1, so your circuit will take this as a 1 and act accordingly. Suppose during this period if the input changes, or if input is not maintained at a proper logic level, your circuit will not respond reliably. So you must keep your input constant during the setup time. Usually this setup time will be order of few microseconds to nanoseconds. During this period your input should not change. If you look at here, this is at logic 1. Similarly, there is a hold time. This is for the input side. When you want to give input to the circuit, your input must be stable for a given point of time during the clock transition. Then only to take a proper input and produce a reliable output. Now let us talk about the hold time. This is the time interval immediately following the active transition of the clock pulse. If you look at here, now your clock is activated. This is above the logic 1 level. This entire region, this is above the logic 1 level. And during this period your input should be maintained at a constant level. If you look at here, this is a constant logic 1, so that your circuit will take this input and respond appropriately. So if you summarize in one place, so this is my clock signal, let's make it 50% here. So during this period your input should be stable, so this will be setup time, and during this period also your input should be stable, so this is the hold time. So as a result your signal should be constant during this period, setup time and hold time, then only your circuit will take this input and respond appropriately. So the manufacturer will specify what is the amount of setup time and hold time for a given flip-flop. This is all about your setup time and hold time. In a straight away you can say your input should be stable a certain period of time before the clock transition and after the clock transition. Now let us take a simple example to understand the setup time and hold time. If you look at here, the waveforms, this is your D input and this is your clock. If you look at here, in the first cycle, if you look at here, this is the setup time, this is the first half of the clock, and second of the clock is hold time. During this period your D input is stable at 0, that's why you are able to see the output at 0 level. But if you look at here, the second clock transition, during this period your input is changing from 0 to 1, so that means your input is not stable during the setup time and hold time. As a result you are not going to produce a reliable output. You can see there is a fuzzy output coming out of this. That's why one should maintain a stable input for a period of setup time and hold time, then only your D flip-flop will take the correct input and produce a reliable output. So in a simplest term, if you want to define setup time and hold time, your input must be stable for some time before the clock pulse and after the clock transition. Then only your circuit will take a proper input, then produce a reliable output. This is the simplest way to understand setup time and hold time. Now we'll see the propagation delay. A propagation delay is nothing but a signal moving from low to high or high to low. When the clock makes the transition, it takes certain time to move from 0 to 1 or 1 to 0. So these delays are measured again 50% of the waveform. Now we'll see what are those. If you look at here, the first one is time delay from going from low to high transition. Second one is time delay going from high to low transition. This is for 0 to 1 and this is for 1 to 0 transition. If you look at here, you have to measure 50% of the waveform, and if you look at here, this much is the time period, this much is the time, a delay moving your Q output from 0 to 1. So it is taking this much delay for changing its output. Similarly, if you look at here, the same thing during the clock transition. So during this time, similarly, if this is a clock transition, again 50% of the time, from where you have to, so if you look at here, this is the time period, this is the time it is taking your Q output moving from 1 to 0. This is the propagation delay moving your output from high to low, and this is the propagation delay moving from low to high. So we have to consider these delays when you design the digital circuit, because this delay, if you add more number of flip-flops, this delay will be added together. At certain point of time, you may not produce a reliable output. So these are the two propagation delays for the. Now let's take a simple example to understand the propagation delay. If you look at here, this is a D flip-flop and this is my D input and this is my clock and this output. If you look at here, so if you take this portion of the time, this is a propagation delay for Q moving from 0 to 1. If you look at here, T propagation delay low to high, this entire time period. And if you look at this one, this is a propagation delay for D input moving from, this is a propagation delay for moving from 1 to 0. If you look at here, this is 1 to 0, and this is, if you look at here, this is a propagation delay for D input from going from low to high. At last, if you look at here, this is the simplest way to understand your setup time and hold time. If you look at here, during this period, if you look at here, you are clocking making the transition. So before the clock transition, your input is stable at one place, and after the clock pulse also your input is stable at one place. If this doesn't meet, then your flip-flop going to do unreliable operation or going to produce a undesirable output. So this is all about your setup time and hold time. Now let's talk about the maximum clocking frequency for the flip-flops. As you know, your flip-flops are synchronized with the clock input. Suppose if the clock frequency is too high, in that case it may not detect the change in the input, because your setup time and hold time will not satisfy the condition. As a result, you are not going to get the desirable output. Similarly, the clock frequency is too low, in a given period of time your input may change multiple times. As a result, you may not get again a reliable operation. The same clock is given to the next flip-flop. In this case, it may not read the correct output from the previous flip-flop also. So we need to maintain a proper clocking frequency, so that it takes proper inputs from all the flip-flops, which comes as a feedback or which comes as an input, and produce the reliable output. This is about a clocking frequency. Now we'll see the pulse width. Now we'll see the pulse width. The pulse width is nothing but the amount of space in which your clock or your asynchronous input are stable at one particular level. It may be logic 0 or logic 1. If we consider, this is the pulse width for this clock at logic 1, and this is the pulse width for the clock to the logic. If you look at here, from this 50 point above it is logic 1, from this 50 point above it is logic 1, anything below 50 points below will be logic 0. So that's how we define the pulse width for the clock. Similarly for the asynchronous inputs also. So this is a pulse width for the asynchronous input. This is for clear. Look at here, below this line is 0 and below this line also 0. Rest above is your high line. That's why I always take 50% of the clock pulse. This is all about your pulse width. Now we'll see the most important parameter, that is the clock skew. Now if you want to understand this one, you have to understand the propagation delay. If you look at here, so there are two flip-flops which are synchronized with the same clock, and you are applying input here and you are applying the same clock frequency here. Your clock is defined as the difference in arrival times of the clock signal at any two flip-flop which are interacting with one another is referred as a clock skew. That means, so this clock, the moment you apply the clock, this will applied here, the same clock will applied here, but there is a connection wire, so there will be a propagation delay. So as a result, your two flip-flops will not switch on, will not start working. So there is a time gap. That time gap is nothing but a clock skew. So depending on the time gap, your circuit may respond abruptly or may not respond at all completely. Suppose if the clock skew is too large, suppose this is the time difference between this clock input to this flip and this flip, let's say large number of amount, let's say 10 seconds. In those 10 seconds, even though this input make a change of this flip flop, their output is generated here. This output will not be applied to this flip flop because this flip flop did not receive the clock because there is a large delay here. So that means this flip flop will not produce a reliable output related to this particular input. If the clock skew is very large, please remember, if the clock skew is very large, the difference in the clock received by the two flip flops is too large. The first flip flop will produce output, but this output will not be enter into this flip flop as it is not receiving any clock signal. So before it receives, the next clock comes, it takes the second input and produces a second input output. At that point of time, the second flip flop will receive the first clock signal. As a result, it produces the previous output, related output, not the present input. That's why there is a problem. So if you want to represent in a pictorial form, if you look at here, this is your clock and this is your clock I and this is your clock J. If you look at here, there is a clear delay in your clock I and clock J. This difference is called clock skew. So now let us consider the case 1 where clock skew is positive. That means your second flip flop will take longer time and first flip flop will take the shorter time. So in this case, your flip flop will take more time than the flip flop 1. As a result, even though if the first flip flop produces output, this output will not be read by second flip flop because it did not receive the clock signal, as there is a lot of delay. When the second clock arrives to the flip flop 1, by the time your first clock signal will enable the second flip flop and takes the previous output and produce output, but the input already changed here. This is the problem with when you have a positive clock skew. Suppose if you have a negative clock skew, that means your flip flop 2 will react faster and your flip flop 1 react slower. That means you are going to make extra gates here so that your flip flop 1 receive the clock signal little late and your flip flop 2 will receive the clock signal faster. So if you look at here, when the clock skew is negative, that means your flip flop 2 will receive a clock signal earlier than the flip flop 1. In this case, before flip flop 1 going to produce a output, your flip flop 2 will take the whatever the previous output and produce output. That means whatever the input you are applied, that output is not established. Your flip flop 2 is taking some arbitrary output which is available at this port, because your flip flop will respond very slowly because the propagation delay for this flip flop is large compared to this flip flop. So you have to consider this clock skew when you are connecting large number of flip flops. So you have to make sure that each flip flop will respond the moment it produces output to the next flip flop. You have to add extra gates or extra delay wherever it is required so that all the flip flops will take the appropriate output from the previous flip flops and produce the reliable output. So that's why your clock skew is very, very important in designing the digital circuit when you are having more than one flip flop. Now let us see the simple example of a data sheet. If you look at here, this is DM7474, a dual positive edge triggered D flip flop with preset and clear inputs. If you look at this data sheet, this is a pin diagram they give for the reference purpose, and this is a truth table for that particular IC. Now if you move further, you can clearly see here there is a TH and TA, TSU and TH. This is nothing but setup time and hold time. And if you move further, it is very clearly given what is the time here. You can see it is nanoseconds. Your setup time and hold time are in nanoseconds. And if you move further, you can see here your propagation delay from high to low, low to high for each input of your flip-flop. We can also see here it is also in the nanoseconds. This is how your your IC manufacturer will provide the specifications for the propagation delay, setup time, hold time, and also they will also give the pulse width also, clock high pulse width and clock low pulse width, and clear and preset also. So this is how you are supposed to read the data sheet for a given IC, and remaining parameters will be discussed in the 5th chapter.